Thanks. So I'm Thomas. My day job is at a IC jazz website, sort of side work. I want to talk about a system called Composer that I've devised. So Composer is a simple, responsive, and extensible system that utilizes structured programming to allow newcomers to explore and learn music rules, mainly rules that we use in the Western culture. So some of the rules that we heard about earlier today, conversation and melodies, the rules that we use in some rules are used there, that will also be used in So this is the first work in this field, in the assisted composition. Teaching there's two ways of grouping the work in this field. So one is on either online or offline composition, the other one is in target audience. So in online or offline composition, I mean is offline, you sit down, you use your tool to compose a piece of music, prior to actually performing it. And the output is a score or a set of notes or what have you. And you take that out and use it to play some music. The assisted harmonization. Online, it's a bit more like having a live context. You're performing live, you're playing music sort of course as you go along. It's more like an interactive jazz session rather than a composition session. And the existing work has sort of been divided between work targeted programmers and people who know how to do computation or how to write programs, or people who are going to learn how to write programs. Or it's targeted musicians. Musicians already have an idea of what is a piece of music. For example, the F-farm, so earlier it's targeted. So if we sort of divide the field of existing work into these two set of categories, there's an offline program, the program is called Shishila, it's written in Oz. It's an assisted composition tool, the declarative implementation. So if you're programming, you can download this link. There's like a load of example code for composing scores. You can sit down and try and compose your own scores using that. But it does require you to be fairly fluent in Oz. Whereas if you're a musician, and you have a piece of music. Last year at the farm workshop, the farm was presented, which is a harmonization program. So you already have a melody, so you're a musician, you know how to compose a melody. You run through this program, it's immediately filed in, it's immediately filed out, and it will give you a harmonized version of that piece of music. In the online context, most of the work is around being into a nice interactive process. So there's this paper called Peaceful Approach, where the authors talk about using closure and overtone to allow people to compose and construct synths directly, and therefore the reader will fit to closure and play it, maybe collaborate with people to play in a nice manner. Though it's been extended in graphical score grammars, where musicians can take the tools, the interactive record, instead of talking directly and typing in code, they use mobile devices to compose structured grammars, and use whiteboards to put those sentences next to each other and make a piece of melodies. But then now, instead of a program, you have a musician to actually do something. And there's references here, and also in the paper, if you're interested in many of these types of work. The composer system that I'm describing today, we're going to talk about today, is aimed at an online context, so it's not meant for offline composition. And rather than targeting programmers or musicians, there's a third group, which is the rest of us. I don't have a strong background programming, not music. It's aimed at people who would like to know more about the rules that govern Western music. What is it that makes music that we like sound nice to our ears, and maybe not to other cultures? What are the rules that govern what we like to listen to historically? So, Composer allows you to play around with 3 of these rules in a live sort of setting. So you can play around, add rules, remove rules, and listen to music and see if you can sort of figure out, okay, what does this rule actually interest? What is music with this subspace of the melody space? What does that sound like? play around and hopefully learn something. The three basic rules, this is targeted around this what's called the tonic note. It's the first note of a scale or mode. It's about modes, so you can sort of select a node, and that defines a subset of the memory space. So then you can select explicitly a mode you're interested in, that given the first node determines the rest of the notes that are in the piece of music that the composer will generate for you. And this is sort of overloading the word cadence. So there's a thing called cadence in the system which indicates special rules on top of the melody composer. So a melody will be a implementation of this scale, but starting and ending on the dominant note, the tonic note. So the implementation of the rest of the notes in the scale is useful for the tonic melody. And if you introduce a cadence, that might enforce some additional rules on particular parts of that melody. So an example is what's it called? The perfect cadence. The perfect cadence, the seventh note of the generated melody is going to be the fifth note of the scale. So in this case, it will be A. It will be the second to last note of the generated melody. So I'm going to play two pieces, one perfect cadence and then one playful cadence. It's going to repeat and see if you can hear the difference between the two. So if you listen to the end of that sequence, that's what alternates. So the idea is that you use Composer to explore these rules yourself. Just try different cadences and see what works, or try different modes or scales to see what's the difference. Can I get an intuitive understanding of what makes a piece sound like as if it's set in C minor. I'm going to briefly describe the system and show you some videos demonstrating it. So the architecture of the system is mainly focused around the JVMs. Most of this stuff lives inside the JVM. The only things that are outside the JVM is the controlling interface. So rather, again, you don't have to program it. So it should be possible to insert this without writing any code. So an interface has been built, an OSC interface that runs on mobile devices has been built where you can select different rules. You can select your tonic note, you can select the mode, and you can select cadence, the piece you're playing. That information is sent using the OSC protocol. The OSC protocol is for controlling music devices, like synthetic music devices, synthesizers, or lights, lighting systems, or whatever you use it to put buttons in, or gauges, or whatever you want to control. This protocol normally listens to all protocols. In this case, it listens to UDP. UDP sends stuff to an OSC server, so it sends signals indicating, okay, the user press this button, this button, this button. That information is sent to the C server. The C server talks to a listener process in here. All of these processes are decomposed running processes to allow for greater decomposition in the system and to allow for the system to be designed in such a manner that it remains responsive. So all the full arrows here, or synchronous calls to send information to the system, all the hollow white arrows or asynchronous calls which can drop messages and stuff like that according to settings to guarantee that the system remains responsive and uses exactly. So that's one of the design goals. It needs to be responsive, easy to extend, and intuitive. So when button presses come in, they get interpreted here into a domain-specific event. It's into a loop that maintains the instance state. Which node is selected, which mode, depending which cadence. Any of these can be set again, in which case you just control any melody without this particular loop enforced. When a new instance state is generated, it is put down to the composer loop, which runs a piece of logic to generate a new random melody. The melody, once it's generated, is pushed down to the overtone loop. Overtone is a library that communicates with supercollider to play music, synth player, and overtone just dictates what music to play inside. Supercollider does not run in JVM for timing issues, just JVM is for publishing timing issues. And I stated like these asynchronous calls can drop messages. So if you change the instrument state 3 different ways before the composer loop is ready to pick that up, like intermediate updates or drops. You only see the last instrument state that exists. This is not using communicating actual processes. Really nice abstraction. Really good decoupling method for building systems like this. The composer loop down here, so the brains of innovations, is implemented using logic programming, and it's implemented using the core logic library, which is an implementation of a mini-dependent system. There's 2 main rules. So you write a program, you declare a set of constraints that you want to be called for any output that thing generates. And you can write helper restrictions, like recursive helper functions, to help you define more advanced rules. In this work, there's one built-in restriction that's used for the mutual. This indicates that 2 lists of permutations of each other. And there's a Scaleo restriction, which indicates that this sequence of nodes is with this scale. So if you have that scale restriction and the permutation restriction next to each other, that's almost there for generating melodies from scales. We're using logic programming to allow us to decouple the actual rules, what indicates that the melody is a pleasing sounding melody. Decoupling that from how we actually go about finding those. So logic programming gives us search algorithms for free, or you don't have to worry about looking through the search page. You can just focus on defining the restrictions, much as it's on difficult, but using a different set of tools to achieve that decoupling. This means that we can take our rules and generate logic programs and run them. So run star will run a program. The program is defined down here. It says, I don't want the nodes to be a scale starting in C3 and should be a major scale. And there's no output on them, right? Because you're just defining restrictions. So this thing says nodes should be a C major, and there should be 8 nodes. This will generate. There's only one software here. I'll generate this scale, right? But there's no. The unknown is what you want to extract from the logic program. Right? You can dictate any of these. You can say that I already know the nodes. I just want to know what the scale is. I already know the node and the scale. What's its setting? You can substitute any of these items. Here we're using it to generate 3 different melodies. So we're saying, all right, I want 3 melodies set in C major. The melodies are permutations of the scale. I want it to end and start on the first note of the scale. Right? And similar, that's what we're basically sort of 3 in the top, right? The first and last tone has to be the same as in the scale. And then generates, in this case, 3 random melodies. Very similar. It's just a small and chasing the air, some other stuff. But you can just add more rules. It's very flexible. You just add rules, you just add restrictions, and then see what comes out. If you add too many restrictions, maybe not what comes out in this case, get the energy backtrack. And again, this is a logic program. You want it both ways. So you could ask it to generate the sort of pattern behind the internal representation of the pattern behind a major scale of behind a melody. So here I've just fitted a melody from before and said, all right, can you just tell me what's the tonic note and the pattern for this melody, and we'll give you the tonic note and the bit pattern that corresponds to that scale. So you can run it both ways. If you're given a piece of music, you can figure out which scale it's actually set in by using the same rules. So that's some of the power of declarative logic programming. It's accessed in a very extensible way by using functional programming. So it's a narrative of two good programming paradigms. It's highly extensible because it's functional, and it's highly declarative because it's logic programming. The code itself is actually quite brief. This is all printed on one slide. It's 150 lines of code. You can disregard this thing. This is all synchronization code from the rest of the system. It's just interested in the brains of the actual composition engine. It's about 150 lines of code. And most of it is fairly obvious. Some of it's even the example code around here. So it's a very small, concise piece of code to call this, which means that you can change it to encode other rule systems, other music systems and Western music. This is just Western music. You can add stuff to this. If you want to add harmony or tempo and rhythm, you just add it to the set of restrictions and just generate melodies that are so simpler. The system itself, when it's up and running, looks a bit like this. So this is the your scene interface is drawn in an app, available app. It's called Touch OS. It runs on Android and iPhone devices. It's just drag and drop, draw whatever you want, and then go and make the OS code. Very easy to get going. There's two tabs. The one you're talking about left one. The right one is for custom putting rhythm. Rhythm is very difficult. That's what we discussed today. So I don't do rhythm. You have to put in rhythm yourself. But here you can control the restrictions. And when you run it, you just sort of click stop. You can deactivate moves already running, and we'll just respond to the melodies. So now we're picking this major sharp. This one now has cadence, so now it indicates what the cadence should be. Again, there's no harmonization as opposed to what we saw previously. Right? So one of the main design goals is to have an active system. So two experiments were designed around that objective, because that's one of the key things is to be a pleasing experience. We want an experience to figure out what's the sort of size of the memory space and how much of it you explore. So when you use core logic will give you the same sequence of results in time. They give you a set of restrictions. There's not never randomization built in there. So you have to generate a large portion of the space and then sample from it to get a random in the process. So the first experiment was designed around figuring out what is the size of the memory space like. How much of it can you actually enumerate and select randomly from and still have a responsive system with today's hardware. And experiment 2 was focused around, okay, given the sort of illustrations before, what's the reasonable amount to set on the size of the memory space that core logic should enumerate for us, and then we still have a responsive system. So core logic doesn't take like a timeout or anything like that. You can only define the size of the sample space. So you have to define the size of the space rather than the time of it. So the first experiment, different combinations of parameters were tried out. So if you have no scale at all, then the rest of these things sort of lose meaning and the search space becomes perfectly big. If you want to enumerate these entire spaces, the entire size of the space, it will take you around 800 days. So that's not a responsive system, unfortunately. If you define a scale, in this case major scale, the size of your memory space shrinks dramatically. And you can enumerate all of it within 5 seconds on this piece of hardware. So quite quickly. And if you add a tonic node as well, the search space shrinks even more, and if you start adding cadence, pure values will be in there. Speed doesn't follow the size of the search space. That's because of the order in which core logic evaluates rules when it does a search tree traversal. But this seems to indicate that it should be possible for us to have a responsive system where we get the last portion of melody sounded. The second experiment has the same set of different restrictions. There's 4 different experiments. We're trying out different search space bounds and measuring what was the enumeration time for each of these. And you see the 2 most restrictive systems, the 2 most restrictive rules. For flat line around here, but the search space isn't running large. Putting additional bounds and it doesn't do anything. So we can enumerate, if you have 2 restrictions, you can enumerate all of the things come out within 300 milliseconds. The other ones are just going to keep climbing. The one with no restrictions is going to keep climbing. But if we set the restriction on 1024, melodies will still get like a fairly large portion of space, not proportional. Still get a lot of melodies, and we'll still get it within 200 milliseconds. So the search space bound is chosen to be 1024 with these experiments. So the conclusion is that the composer system tool demonstrates it is possible to build a responsive system that's interactive and where you can keep the core quite small and clean, so it's easy to extend. You don't have to change other stuff. You just it's additive only. It's very easy to add stuff, very easy to move stuff in. And you can add other types of music to it. So I've only been exploring Western style music. I didn't know anything about this before I went to this school. But you can take any music system and just change those 120 lines of code, and you get a new exploratory system. Oh, I need to this. Yes, different types of parameters and different types of music. The future work is probably going to be focused around this search space, right? If it's 25 to the power of 8 in size, and we're only sampling like 1024, it's a very small portion. Again, unfortunately, the logic programming doesn't allow you to arbitrarily pick just one element, and even if it did, I would assume it's very difficult to write an algorithm that gives you uniform sampling and stuff when you can when your domain space is like arbitrary. Another interesting thing would be to look into would labeling these things. So there's no labels in this page because it's meant as a very exploratory tool. When you start adding labels, people focus too much on the labels and instead explore the rules and figure out what's going on. As I've said a couple times, non-Western use is very interesting to explore, but none of this will really make sense without any proper user testing. Put this in front of kids or people that go formal music training, let them explore it and figure out, right, can I decipher any rules? No, does this make sense to me? And what doesn't make sense? And if you can do with other rules that are more that gives people a better intuitive understanding of what's going on. Of course, as we talked about before, harmonization is very interesting. Post-processing stuff is very where you could enforce it at the same time. Rhythm is very interesting and very difficult. So rhythm will also an obvious place to extend this work. That's it. Thanks.
I'm curious about the marriage between logic and functional programming, and my question is whether the tie-in has some kind of deep principle reason, or rather it's a kind of architectural / engineering / matching thing, or because
why the logic programming was
why you chose to go that way to do to use a logic programming library in Haskell rather than saying, well, I'll do that layer using Prolog, for example, something like that.
Oh, so the core is this, by the way, I'm putting it into it. This is written in Clojure, so it's this implementation. And I wanted to use a declarative engine because I wanted to separate what the music was and how to search for music. I think it's a sound engineering practice, and it allows you to write a very succinct small core that you can pick up without, you don't have to think about search-based information. You can still pick up that part of the system and extend it. So one of the design goals was to have an extensible system, and that's why I'm married into using declarative programming so that we can do that sort of stuff. Yeah.
I'm interested in the overhead of the mini Conran system. So how does it scale? Where is the overhead going to be too much? If you go past 8 nodes, for example, or something of that nature?
I haven't tried out anything about 8 nodes, to be honest, but it's a very efficient core, mechanical core. I don't think I'll be limitation itself. To correctly determine that this thing, it's probably try running against Prolog. It's just like screen out which one's going to take a hit first. But there's some. If you're interested in the performance of Prolog, there's some good talks around solving the separate process.
It's just, I find it very brave of you to put logic programming into a system which has interactive real time.
Yeah, that's exactly why the experiments were there. Right?
Yes.
You know, this is actually responsive. Yes.
Some people would say that about any functional language as well.
It's the next generation. It's the next generation of fear. This one. So we're just trying to push it. Yes.
To kind of relate to that, your way of exploring the search space by enumerating all sorts of random junk and then throwing those away.
Yeah.
I thought that would really dominate the cost of using one programming language over another.
Yes. Yes.
But you say you don't want to tangle these together too much. You don't want to have something that is a non-backtracking enumeration so those people can come up with.
Well, I think the problem is that you always want a fair, unbiased sampling, right? And when you want unbiased sampling, then requires you should have noise or incorporate noise into your sampling structure that has to do with your domain. And I can't really do that in the logic program because I can't really change the search algorithm directly. Even if I could change it, whenever I change the rules that govern what decent sounding melody spots, I would have to change the rules that govern how I perform my search to maintain an unbiased sampling. I think that's the problem, right? You can't get unbiased sampling unless you know the domain. So making the choice of having unbiased sampling would require me to always have those two things bound tightly, which makes me point here.
So it's related to what Pedro showed with using quick checky kinds of things and weights on the rules in quick check.
Yeah. That's one way of solving it. Yeah. But again, it requires you to be intimate with your search algorithm.
Yes, and it also doesn't directly relate to the probability distribution over the sample space. So it's quite hard to get the numbers right to get the
Yeah. Exactly. I think,
do you have a commercial application in mind, or is this a commercial application?
this is an altruistic project. My commercial ambitions were no further than maybe taking out to some schools and have kids play around and figure out, okay, this is actually
Educational.
It's educational, yeah. I don't have any commercial plans for it. Yeah, I think you would be able to build something that's interesting. I was more thinking of either educational or an art installation of some sort that allows guests from the museum to explore museums and get instant feedback. I think it's time.
All right, thanks.